Can you make these things organically, or are they still inorganic?
Memory systems. Those are inorganic, but they are examples of organic memory systems already.
That looks like an fMRI, that little thing in there. So
yeah, that's why I used that picture, not to distract you. So this is part of my work. So now after going over all that, so what I can show you right now is I cannot show you interesting applications like image classification with membership networks or even speech recognition. Because at that point, we are still trying to figure out how do we connect the networks, what type of capabilities do they have. So for now, it's just some theoretical measures that we try to get out of them. So we model the network. So here the bigger red dots on the right, they relate to the wires that are underneath. They're upwards connections where you connect the CMOS interface. What you mentioned that you have basically the reservoir which you connect to some standard computing architecture which can actually compute it reliably or which can compute with a higher precision and where you can implement weights that you can precisely control. And on the left side is basically an example of a beta distribution where I can play around with how do the statistics of the length of the connections is, or the statistical distribution of the connection length. Right, with alpha and beta, I can move from purely locally connected, similar to cellular neural networks, to completely only global connections and a mix. So basically anything I want, I have two parameters that I can define a different network topology. And so then based on alpha and beta, we try to measure the entropy, as Andy was mentioning. So the entropy that, in a sense, that we apply an input signal, and we measure how much does that input signal is transformed within the reservoir. So we have our 16 nodes. We apply the input signal to one of them. We have another one that is your electrical ground, and the other nodes are measured, and we do some correlation measures and see how different they are. If they are all linearly dependent, then your system does not. All right.
Did the computer just die?
Yeah. Right, no problem. So we have a network that we stimulate at one point on a physical location, and then we observe the rest of the network. And if we can observe non-linearly correlated behavior, we are close to getting some reservoir properties that we talked about earlier, some kind of separation properties, that different locations in the network, they actually give you different representations of the same input. So that's something we want. And so what was shown in the data is that purely or very locally connected networks don't do very well in the sense of creating information, which is maybe a bit counterintuitive to, let's say, cellular neural networks, and it comes from we using a completely passive electrical network. So in a neural network, you always have your weights that can amplify signals. Your activation function will always get your output between -1 and 1. But in a resistive network, you don't have amplification. So you basically just, depending on the number of connections you have, your relative voltage applied to each device is getting smaller and smaller. The more devices you have in the chain, basically. And with completely locally connected networks, you have a lot of devices between your input signal and your ground point. And then the voltage that you apply to each device becomes very small, and you don't get the nonlinear switching behavior that you actually want to harness it for computation. So those were some interesting points that are not natural to other neural network types of computation.
We were said the computer needed to be updated right now. That's what happened. Thank you, Microsoft.
But we're using Ubuntu most of the day.
No wonder there's a lot of Macs in here, pretty much anything else but PCs, right?
No worries.
So if you have to learn from the reservoir itself, how much like extra computation do you really get? Like a little bit. It's hard for me to wrap my head around what the transformation really gives you. Like how it does the computation, other than just creating a pattern, but you're being, like your eardrum being or something like that.
So for the memoristic reservoirs at that point, I cannot give you precise numbers, but going back to the basic reservoir applications or implementations, the neural network implementations, what you achieve with reservoirs is that compared to feed-forward neural networks, for example, or if you have temporal processing with Markov chains as well, you might use a few more components, maybe twice as much or 3 times as much, but your actually training complexity is much smaller.
Okay.
So this is what you gain, that you reduce the training complexity, the training time, as compared to networks that like just regular recurrent neural networks that you train with backpropagation.
So like a really good filter, just like it spreads it all out so you can pick out kind of what you want easier.
Yeah, that's the ideal situation, right?
Yeah.
So with this work, I'll try to get there eventually to be able to understand what makes a good memoristic reservoir, what helps to separate data,
and that's what this is with the entropy stuff.